to take stock of where we are, you should feel, and from the test, it looks like you do feel. Generally, with with a few little things, but I don't really care about little things, little mistakes, little. If you can look at what I said on your test and go, oh, I get that now, then it's high fives all around. So you understand how to calculate strain. The idea of strain is something is going to get longer or shorter if I put forces on it. And the idea of stress, which is I put force on something, but I don't just consider the force by itself and say 1,000 pounds. I consider it as a function of the area that I'm putting it on. Like snowshoes, I can walk in the snow, but I weigh 170 pounds and 1 foot in the snow, it's going to sink in. But if I spread that out, all of a sudden I don't sink in because I'm taking the same weight, but a larger area. So that's why stress is such a cool calculation, because it normalizes it to per square inch. Every single thing is per square inch every single time. And so this is kind of cool. What I stuck up here, this is a couple of things kind of straight out of your book. But in order to get these calculations, they literally test materials. And so this little, cartoonish drawing right here, they take this little dude right here, and notice how defined it is. This thing is 0.5 inches in diameter, and it's 2 inches between a couple of dots, and it's got screw threads on both sides. Why would it have screw threads on both sides? Well, if I take this pen and I grab onto it, does it make sense? If I don't have a very good grip, it's just going to slide off. So it's like, how do I grab onto something to pull on it? Well, if they threaded both sides of it, then you'd be able to basically screw those into both sides of this, and then you could actually pull tension on something. Now, what's going to happen if you pull tension on something? Well, that's what this figure down here is showing you. Notice microscopically, if I pull on it, it's definitely going to get a little bit longer, but that might be very hard to see. So does it make sense? You might need some kind of a machine. And from what I've understood, actually just reading your book, because I'm teaching this to myself, is that little 2-inch distance right there, they actually put a couple of like electrical beads on both ends of it so that it's actually able to measure it. It's not like you just put a tape measure up there and try to determine how far did it go. I mean, they're putting, it's very precise, because something that's a 1/2 inch in diameter steel, you can appreciate that's not going to want to stretch much. Like you and I pulling on it, it's not going to move at all. But notice at some point, this is kind of cool, it ultimately yields and kind of creates a neck in it, so to speak. At that point, like, oh, you've damaged it now. Like if that's your bridge, we don't want that happening, right? We don't want so much force that happens, because the steel's no longer the size it used to be, which means it's not going to be able to do the same job tomorrow that it did today, right? And so this business of materials testing. So really what you're seeing over here, what you're seeing here is tension. You pulled those two apart so that a neck formed in it. But notice this isn't tension over here. There's not a way to grab concrete to actually pull it in tension. I have seen this done for real. And this is exactly how it looks. When I mentioned to you before, they take 6-inch diameter by 12-inch length cylinders, and it's a piece of plastic, and they just pour the concrete in it, and then they tear the plastic off, and now you have that piece. And then they set it in this and start pushing on it. And concrete typically, for, as I've mentioned to you guys, is calculated to be 2,000 PSI concrete. And that should mean something to you, whereas the average person on the street, including me, until I started learning this class, that didn't mean that much to me, just other than 2,000 is good, 1,000 is not good. But you can see with the top of that being 6 inches in diameter, does it make sense that's not 2,000 pounds pushing on it? Because that's not 1 square inch. So there's a lot more than 2,000 pounds up there. But basically that right one where it finally went and caved and failed and gave out, you would hope that if that said that was 2,000 PSI concrete, that didn't break until more than that. Because remember, 2,000 is the promise. It's okay if it breaks more than that, stronger than what you promised, but you can't under deliver and over promise. So in a sense, that's where we're going now is, yeah, well, if I put force on something, it is going to get longer. Does it make sense those would be related? Like if I put more force, then it's going to get more longer if I'm stretching it in tension. And so, is there some kind of relationship between those two things? Like it takes force to cause something to change size. We've been studying those two independently, right? Well, now we're going to study them together. How does a certain amount of force cause a certain amount of change. And it turns out the relationship between those is really simple for a while and complicated ultimately. So let's take a look at in the sheet you have. I hope I have it here. Don't put it. Which one is it?
Out of curiosity, I haven't looked at the videos. Does the concrete make like a loud noise when it fails?
Yeah, it's got a door around it because it'll shoot concrete all across the room and like go into your skin like it is gnarly.
There's this YouTube channel where I think it's literally called the hydraulic press channel.
I've seen that.
And they just crush ridiculous.
I was telling them like tubes of toothpaste and stuff.
Or, yeah, and they'll get like solid balls of like titanium.
Oh,
It's always super loud.
I haven't seen that.
They have the,
I've only seen like the easy stuff.
yeah, or they'll crush like just ridiculous
Yeah.
toys and stuff.
Okay, so look at this sheet. Like we got to get really familiar with this. Let's see what I gave you there. That's titled like the note sheet for this whole section, right? Something like that. But this is what's really interesting right here. So this took me a while to get my mind around, and I don't have it memorized, and I don't even know if I want it to get memorized, but I want you to spend quite a bit of time staring at this. But notice what this thing is called is a stress strain diagram, as it says up there at the top, because stress and strain actually are related to each other. And this graph is going to show you exactly how. And you need to understand that this graph came from putting those pieces of material in there and just stretching them and saying, okay, let's put 2,000 pounds on it. All right, how much longer did it get? All right, let's put 6,000 pounds on it. How much longer did it get? Well, it turns out for a while, and you need to notice this really carefully here, but notice this x-axis is labeled with epsilon, and this y-axis is labeled with sigma. And notice I'm reminding you because the number of those letters is awful overwhelming. It's like, oh yeah, that's right. Sigma was stress. And that's right up here at the top. Stress was a force divided by an area. And I'm reminding you of units, and strain was epsilon. That's right, which was the change of length divided by the original length. So it's a percentage in a sense. And so this is literally a graph of what a material looks like when you do put that test on it. And so notice excuse me, and one thing about this that bothers me as a mathematician is usually X is the independent variable down here. And like, that's what you have control over. And then the other thing happens as a result, the Y happens as a result of that. But this is actually backwards. And I actually don't have a good answer for why that is. The reason I say that is don't you have control over the stress? Like you can actually put as much stress on something as you want, but then doesn't the lengthening happen as a result of that? So it's kind of backwards. So notice what happens over here with respect to stress and strain. Do you see how the relationship is actually linear here? That is really cool. And thank God it's that simple. It's linear for a while. In other words, if you double the force, it's going to double the length. Triple the force, triple the length. Cut the force in half, length gets cut in half. It's linear.
Are these all measured? In the
Yeah,
machine?
literally measured. Like you pull, one of my favorite ways to think about the universe is like human beings, and maybe I said this in here, human beings are like given this ball of dirt, and then we just dug around in it and found like a car, like all this cool stuff that we made with our brain and the resources that were in there. But it's literally like digging stuff out of the ground and saying, yeah, this has got interesting properties. You know, this thing would be good to hold up a car that wants to try to get across a river because it's really strong, you know, whereas this other stuff, not very strong, and it falls apart really easy. So yeah, it's literally just grabbing something you found out of the ground and pressing on it and measuring what happens. So there's no math for this. Does that make sense? Like there can't be. That's fascinating. And then of course, you know, we have alloys at steel, which is where we find a few basic metals in the ground, but then we mix them together because then it gives them these properties that makes them more flexible than normal. And, you know, so it took the ingredients and made other things out of them, just like you might for a recipe for a food or something. But this is huge right here. Modulus of elasticity, E. If you take the ratio, stare at this little formula right here. If you take the ratio of the stress divided by the strain, you always get a constant. And that's exactly, that's why that line, that's why that's a line. Do you see that as the same thing? E is just a constant number. If you double sigma and double epsilon, you get the same exact answer you had before. You get a constant, and that's the slope of that line. Notice in that diagram over there, that's kind of what it shows. E is the rise over the run. E is the sigma divided by the epsilon. So sigma divided by epsilon is actually that slope. So it's actually the slope of that line is what we call E. Now, this is a number I've used a ton in my life, but I never understood what it was and where it came from until now. And so that number is described as the modulus of elasticity of some material. And it basically just means what it says. It's elastic. How elastic is it? You can appreciate with a rubber band, and I have to put very much force on it to make it get a lot longer, right? But if I did that with steel, it's not going to get longer at all. So how elastic is it? If you have a big number, it's not very elastic. If you have a small number, it's pretty elastic. Rubber band would have a small E value, steel would have a large E value. So it's how elastic is it? And so for different materials, notice this drawing shows the slope there, but does it make sense something like balsa wood would look like that? Because it would have a much lower E number, whereas something like, you know, high strength steel might look like that. Like every material just kind of has a slope there after you pull and push on them inside that machinery. And so modulus of elasticity is a huge calculation. It's a gigantic part of what you do. Now, just for the fun of it, in the back of your book, this is on the back page of your book, and I'll probably give you a copy of this because not everybody has the book and so forth, but just as an example, and we're going to need to use a bunch of this stuff, but notice these two charts are identical. One of them, though, is US customary foot-pounds R system, and the one down below is SI units. I forgot what SI stands for, standard industry or something like that. That's kind of the metric one. Yeah, I think that's right. Thank you. Notice right here is the modulus of elasticity. And notice they're really big numbers. So notice that says times 10 to the third KSI. So K is already 3 zeros, and this is times 10 to the third. That's 6 zeros behind whatever number you see down there. So whatever this item is, it's 10 million PSI. That's its E value. That's its flexibility or its elasticity number, 10.6. What is that? Something called T6 2014 aluminum. So, I mean, I've heard of aluminum, but I don't know what that is. Notice there's copper, magnesium, steel, a whole bunch of different steel alloys, A36, A992, like those come up in a bunch of your assignment questions. Because they'll start to say things like, and we've been talking about this, but the concept that it's like, oh, okay, I got 4,000 pounds on this bar. Well, at some point you got to go pick one, right? You got to go find a bar and choose its diameter. Well, if you say, okay, let's use A36 structural steel. Okay, well, that's cool. Right there, it says it's 29 million PSI. That's how strong that is. Notice that's one of the larger numbers on the list. Actually, is there a larger number on that list? It's called structural steel. I think of steel as being strong, and then it says structural on top of it. In a sense, that doesn't surprise me that that's sort of like the winner, right? And it actually is. I never looked at that before. But maybe you know aluminum's a little softer, like you can actually scratch aluminum with like a knife, but you're not going to have such luck with steel. Is there any tiny numbers up there?
Oh, yeah.
Yeah, like wood. Douglas fir here is the tree that goes around here. And so everything that's built out of wood that's structural around here, Douglas fir, because that's what trees grow nearby. If you want to ship it from China, it's going to cost 3 times as much. So that's what we use. What
Surprisingly high numbers.
was that?
1.9 million PSI.
Yeah, notice it's still almost 2 million PSI. That is remarkable, isn't it? I mean, that literally means if you have 1 square inch of it, you can put 2 million pounds on it before it, you know, or I shouldn't say before it breaks, because that's not really true. That's not stress, but that's its slope number. That's its relationship, its flexibility, if you will. And so, yeah, that's still a really big number,
Out of
right?
curiosity, if you build like a mansion, somebody, a rich person house, like 20,000. Are you still using like Douglas fir if it's like a 3-story house?
Yep.
Or you are?
Yep. I mean, you can do steel studs, but the only advantage of those is they're nice and straight and they're fireproof.
Right.
But they cost a lot more, but inside you wouldn't notice the difference. Structurally, they still hold just fine.
Don't we want with the tall buildings flexibility associated with it? Skyscrapers, or skyscrapers make a brick room like 10 stories tall, right? And then they would like crack under their own weight.
Yeah, that's right. The old structures that were made out of rock were not real good when any kind of seismic, any kind of motion of the earth, they want to crack and lose their structural
Do you
integrity.
take that
So
into consideration when you're building a home that's only 2 stories high?
not when it's like 1, 2, 3 stories high. It starts to get serious when it gets tall enough that it actually kind of has room to, do this. Like even grass, you see it blowing in the wind if it's tall enough, but if it's not that tall, like your yard, that much. So for now, just notice that there's just a lot of cool things in this chart, like how much does it weigh? That's kind of interesting, isn't it? Because in the end, I'm going to build something. If you use a certain one, it's like, oh, that weighs, this many pounds per cubic inch. So you can actually figure out how much something weighs just by that kind of density number, if you will. It's kind of like telling you how dense it is. So if you can figure out how many cubic inches of it that you're speccing for something, then you can know how much it weighs. And how flexible is it? Something later on we'll be talking about modulus of rigidity, how rigid is it, and so forth. And then there's all these things about yield strength, like how much can it handle in, well, you should recognize all those 3 words right there now, right? You just calc that on this last test: tension, compression, shear. Those are some of the classic forces that are on something. And so, how much can it handle in tension? How much in compression? How much in shear? But then it's like yield strength, ultimate strength. Like, what the heck does that mean? Poisson's ratio, that's coming. Coefficient of thermal expansion. If it gets warm, how much does it expand? Some materials expand more than others. Notice percent elongation in a 2-inch specimen. I don't know what's elongating it, but that sounds like a strain, right? Like something elongating. 2-inch specimen. Well, isn't that what I just showed you a second ago? That distance between those 2 points on that deal. That must be the percent elongation for a certain amount of like a force that they use every time or something. I actually don't know. But the point for now is just this is the single most important number on this chart, is the flexibility, the elasticity number for a product. So this equation is gigantic, and notice I even wrote it 2 different ways for you here. I wrote it over here on the right. And let's take a stare at the units of this for just a second. Do you remember how epsilon over here, if I write it like, if I look at this version of it, you're bigger. Epsilon was unitless because it was a percentage, right? And sigma on the other side was PSI. So does it make sense? E is also PSI, kind of by default. So it's also pounds per square inch. And so Hooke's law, you may remember from other places, it applies to springs and all kinds of things, but it has to do with, in the case of a spring, if I pull on it with a certain amount of force, and it's going to get longer, but then if I double the force, it'll get double its length, just like what we're discussing here. And so there's a proportion. Something being proportionate means, hey, those 2 things are related by just 1 constant. All I got to do is just throw a constant in there and they're the same exact thing. Well, that's what we're defining E to be, is the connection there. Of course, there would be a connection between stress and strain. If I put more force on something, it's going to change length more or whatever. Yeah, that makes sense. But the fact that it's linear, like that simple, it's not some parabola or sine or cosine or some crazy formula. It's kind of like, ooh, that's kind of cool. And so that slope of that line expresses what we call E to be. Not that different than pi. Pi is the circumference of any circle divided by its diameter. Pi. The only difference with pi is it's always pi. E is not the same for different materials. Now, let's just stare at some of these names. Notice over here, there's like all these different sigmas. There's like sigma prime F and sigma U and sigma F and sigma Y and sigma PL. It's like all these different sigmas. But notice, if you just stare at those, just notice they hit this curve in a number of places. But let's just stare at this for a second. So this relationship right here stays linear. So in other words, I put more force on it and then, oh, it got longer. More force even got longer. But notice up here at some point, I didn't put any more force on it, and yet notice it's getting longer and longer and longer. Like that's because it yielded. That's because it failed. Like that's because you broke it. It's never going to be the same again. In engineering, everything lives right here. You don't ever want to have like something on a building that average force on it changes it permanently, because then tomorrow it won't be able to do its job. Does that make sense?
So what the yield stress is when the neck develops on that.
Yeah, that's exactly right. Notice though, necking is actually way the heck over here. So you can actually change something microscopically and not even see it. So necking is actually right before it's just done. As soon as it starts doing that, like 2 seconds later, it's going to snap in half. So notice this curve, if you will, starts out really cool and straight, but then it has like it starts to behave wonky. Like all of a sudden it kind of levels out for a while, which means it's actually getting longer without even adding any more force to it. And then at some point, it's almost like it says, okay, enough's enough. I'm not going to break. And then it starts to take more force to get it to get longer and longer. Notice as you move to the right here, epsilon, the percent it's growing is getting longer and longer and longer. It's just interesting to think like, what does it take to get it to happen? Because like I said, in here, you're not even adding any force. But then at some point after yielding, you jump into this strain hardening area where it actually starts to increase. Like you actually have to pull harder and harder and harder. And then notice, and this is why that's called sigma U, sigma ultimate. Like this is the most stress you can put on it. Because if you go, like it actually starts leveling off. In other words, at this point, because it's reached its ultimate stress, you could actually start backing off and putting less on it, and it's still on its way to breaking. You see what I'm saying? So there's all these interesting points on the curve. This is the ultimate stress. In other words, the highest stress you can actually ever get. Let's ignore this for right now. This is complicated enough without talking about that just yet. And notice this is a good one, fracture stress. Like when did it actually fully break? You saw that concrete a minute ago, oh, exploded, like done, game over, no more testing. It's not even what it used to be anymore, right? Fracture stress, notice what it's abbreviated, sigma F. Sigma U for ultimate, sigma F for fracture, sigma Y for yield, because that's where it actually yielded. Because again, we want all of our products, anything we spec, to live in this world right here. Basically what that means is if you put pressure on it, think of a car driving across a bridge, the bridge goes, and it tries to lift it, and then when the truck goes off, it goes, okay, great, I can relax. And it goes right back into its original position because you haven't screwed it up permanently. So as long as you stay in that straight region right there, nothing kind of gets harmed. It stresses, it bends under the load. We've been talking about all these internal loadings. You put this force on it, it bends down, then you go away, whoop, goes right back into its normal shape. You haven't screwed it up at all. Nothing broke internally. It stayed within its, and you can appreciate wood. You can appreciate wood. Wood's going to pull apart. If I bent it too much, it's going to pull apart. And then when you take the weight off, what happens? It doesn't go back anymore. You broke it now. Does that make sense? It yielded. So now you're in that orange area, that yield area where you've kind of broken it now, and now it's not so good. Doesn't mean it's necessarily going to, fall and everybody dies just yet, which is kind of cool. And you see the factor of safety built in here. Over here, fracture stress, that's where everybody died. But we're trying to stay clear over here, trying to stay way away from that, right? Because we want it to stay, we want the integrity of whatever the material is to stay what it was before. What's the PL? Stare at this. What's PL an abbreviation for? Proportional limit. Do you see why it's called that? Because it stays straight lined until right there, and then it starts to curve. And so we want to stay inside. We don't want to ever put more sigma on it than would be to that point right there, because after that, it's going to start, kind of on its way to yielding. So notice I kind of gave you some sort of definitions down below, or, it's like this is just me trying to process and make sense of this of this graph and so forth, what's happening, because you are asked some questions about different calculations pertaining to where you are on that graph. Notice there's down here, it says, this is the elastic region. Elastic behavior here, this is all elastic, meaning if I bent it, it bends right back. Okay, but outside of that, no longer elastic, it's now called plastic. So there's elastic and there's plastic, and then plastic is broken up into its yielding, it hardens and kind of starts fighting back, and then it's just on its way to breaking and it finally breaks. Like that's kind of the rough logic to what you're seeing across here. But notice these, let's just kind of read them really quick. Proportional limit, sigma PL, maximum stress at which the curve, in quotes, is a straight line. So we're staying there. But then elastic limit, this is the limit before permanent deformation. So this elastic limit right here, it's going to come back as long as you stay inside this elastic area. But you go beyond that, not cool. Yield stress, maximum stress at the elastic limit. In other words, this pink region right here is the elastic region. Well, that yield stress is the stress you put on it that took it there. Does that make sense? So we'd never want to go above that, right? We want to make sure that this is why you see a bridge that says maximum limit 22,000 pounds. It's because somebody said don't go above this, you're going to screw it up permanently. So that's the yield stress that actually took it to that edge of its elastic limit. And then ultimate stress, sigma U, the maximum stress it can bear. And fracture stress, the stress at which the specimen actually breaks after necking. And then let's not talk about true fracture stress right now, but
We can look at corrosion.
not really. That's something that you have to test, because what it's doing is changing the diameter or changing the dimensions. Like it used to be this big, and now because it's corroded, it's only that big. So that's something you have to plan in, like if it's the coast. You can't just say, oh, it needs to be 1 inch, because you got to go, well, 50 years, it's going to be 10% less because of corrosion. So let's make it 10% bigger so that it can still be functional, So
Speaking of, like, you're like 50 years from now, is the middle, you're like, the elastic behavior is where we're good, over on the right is where we're bad. Is all that middle part kind of just like, oh, hey, if you are residing in here at any point, we're cutting years off the life of the object of the bridge or whatever we're doing. Because we're like, and so do you have, I guess, I know we're probably not going to go into it, but like, are there ways to calculate, like, oh, you've spent this much time in the yielding stage that you've cut this many years?
yeah, and of course the main thing is it's not the shape. It's not internally what it used to be anymore. Like the chemical bonds between things are broken in there. Concrete's a good example because it's literally a chemical reaction. And concrete, if you just sat there on the ground and never put one weight on it, it will decompose on its own. So it's not force on it. It's just the internal glue, if you will, just wears out over the course of 50 years. So yeah, you can walk up to a bridge and take measurements on things, and you can't test it anymore because your bridge will break, but you can take measurements on it to kind of determine where it is in its lifespan. And obviously there's huge factors of safety built into that.
So as long as it stays in the elastic region, like even over a span of 100 years, say a bridge, you can, as long as it never exceeds that elastic region, it won't have any permanent damage. Or could it, over time, the more you push, does that elastic region?
Yeah, in other words, does it sort of weaken because you kind of like a rubber band? If you just go doing, like 50 times, at some point, it's kind of like, oh, it's
Yeah.
died. I guess off the top of my head, I'm not sure. It does seem like that would make a difference. I mean, if you had a bridge that nobody ever drove over, it seems like it would last longer than one that somebody drove over constantly, right?
I guess that kind of just ties into like wear and tear.
Yeah,
But that would like make that elastic region smaller.
my guess is yes, yeah. And there is a thing called duration that I've seen in truss design, for instance. And it has to do with the fact, like when you build a house, you put all the trusses up, but then you take the entire load of roof sheathing and you put it in one spot on the roof. And then because the builders have to get it on there, so it's not there very long, but then they grab those sheets and one at a time, they take them across the whole roof and sheet the whole thing and spread the whole load out. And so it's got to be designed to kind of handle it point loaded, and they don't spec like it's got to be right here. This is where we strengthened it. But it will handle overloading, but just for kind of a shorter period of time. And that kind of makes sense too. You're like that too, right? I can lift this weight, but I can't lift it perpetually. So, materials have a similar kind of a similar way of operating. So you'll find that any questions in this next little bit that kind of puts you out here, you'll find yourself staring at this, trying to figure out, wait, what ultimate stress, like what? Because there's so many different sigmas over here. It's like, what, which one am I supposed to calculate? All that. And a lot of them will be, they'll give you a stress strain diagram like this, but it'll be for a particular metal. Like this is just generic, showing you what all materials kind of look like. They kind of take on this basic shape, but if they show you a particular one for a particular specimen, you can actually read those things right off of it. If it's scaled well and you said, hey, look, there's the top, and then you looked over here and you could tell, oh, that's 16.2. Well, then if they say, what's the ultimate stress? 16.2 PSI.
Was at that point taking the test.
Right enough.
Yeah, exactly.
So you'll need to spend some time with this chart. But the cool thing is, as an engineer, all of our calculations are going to live on that red line, and it's not near as complicated. And because I have this basic equation right here that shows that stress and strain are actually related, and they're very related in a simple way, which means if I know the strain on something, I can actually calculate the stress that's on it. Or more importantly, I know, because I know how much things weigh, I know how much stress this is going to put on this member, and then I can tell ahead of time, oh, it's going to get this much longer. So they're related, and that's powerful. Does it make sense? Like you need to know how much longer something is going to get, because it could fail because it got longer. Sometimes you can't, sometimes that's not okay. So there's got to be room in the system for that. And you notice on the test, that's what happened. Like we didn't talk about stress on it, but I forgot which question it was, but toward the end where there was force on it, and that cable got longer, but there wasn't anything said about what the stress actually was that caused it. Well, this section is just going to say what stress, if you put this much stress on it, then how much longer is it going to get? And you can calculate that ahead of time. Does that seems powerful, doesn't it? It seems like, wow, that's rad. I can figure that out. And I can see an engineer would need to know that. Take a look at this other rad stuff. So notice this says this is a typical stress strain diagram for mild steel. I also stole this out of your book. You can appreciate this. How am I going to get a hold of something like this unless I was, a materials tester myself? But I want you to stare at this a little bit, because this is an important part of your assignment. Notice it says up there, the elastic region is enhanced in green. Do you see how that elastic, just look at the blue, ignore the green. Does it make sense? Like, whoa, look how steep that blue is right there. It's almost like straight up and down. But do you see the same things we just saw in that previous figure? In other words, it's straight, 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 straight. Then there's a little curve. It's level for a while, and it kind of bows up to a max and then goes down again. Like this is the same shape we just saw. This is what stress strain diagrams look like. Now, since we said that this part right here is kind of the important part, where stress and strain are related based on E, modulus of elasticity. It's like, I can't read this chart. That's too steep. I can't even read it. So what do they do to make my life a little easier / a little harder? They took just this part of it right here and expanded it. So notice the black numbers down here. It's like this is worth 0.05. That's 5% increase in strain, right? It got 5% bigger. This got 10% bigger. This got 20% bigger. This got 30. Well, in order to see this part right here, do you notice in green, they relabeled the exact same marks. So this label, which on the blue graph is 0.1, is 0.001 on the green graph. Notice that maybe here I could actually determine the slope of that, because I can actually see it, but I'd have to be looking at the green numbers. Does that make sense to be able to do that?
So it looks like the y-axis is still the same. So
That's exactly right. They did not change the y-axis at all, but they did change the x-axis. Good job. And notice,
take 2 points, like 10, 20, and then that'll give you your slope, right?
that's exactly right. And notice they even were nice. Like this point right here looks to be the place where the straight line ends. Do you agree with that? And so if I look down here, it's like, oh man, how do I read that? Well, they told me. They told me what the reading was, because if I knew it was bigger than 0.001 but smaller than 0.002, it's kind of hard to tell where I am. So maybe they'll just tell me. That's nice. It's a hair bigger than 0.001. Oh yeah, 0.0012. That is a little bigger. I can see that. So I know it starts at 0, 0. So if this is its x coordinate, it's, well, epsilon. And notice over here, they did the same thing. It's kind of hard to read. So it's like, oh, look, they told me sigma PL, proportional limit, the end where this is straight, proportionate. They just told me that's 35. Well, since my did my formula say epsilon was sigma over epsilon? I'm sorry, I said that wrong. E, modulus of elasticity. I'll write it down. There's no reason I can't write it here. E was sigma divided by epsilon. Do I have that right? I'm actually pretty sure. By the way, one of the reasons I keep that straight is because of units. Does it make sense? E has PSI for units and so does sigma. And then epsilon is actually unitless. So does it make sense? That would have to be, the sigma would have to be on top for those units to work. So can't I just read that off of that green graph? So isn't that like 35? But notice, what are the units of that? KSI, so that's actually 35,000 PSI. So now it's PSI. And then I'm dividing by the epsilon that goes with it, which is 0.0012. I'm going to get a really big number for that. What do I get?
Yeah,
I'm going to write it. Tell me.
291,66666.67. I was like, 100,000.
So notice that's PSI. So if I put commas in there, that's like 2.9 on that chart we just looked at a minute ago. 2.9 million pounds per square inch. So do you see, like, can you see that you literally would have to have a materials tester and pull on it and literally take measurements? How much force did I put on that and how much longer did it get? I literally got them from that graph that I made of the data that was pouring out of the machinery, if you will. And if I can read it, if I can find an XY coordinate up there somewhere before that plastic or before that proportional limit, any place on there, I could have read it right here too. Do you agree with that? Does it make sense? I could have read it right there if it was possible. You can read it anywhere. And I divide those two. Notice I actually have a reasonable number. Now, does it make sense? You would not go to the back of the book and say that the E number for this is 2.91666667 because the piece of steel you have here won't even be the same as the next one that came from the same ground. Like all trees are different. And so they would probably just call that 2.9 and round it off, right? Or maybe round it down a little, 2.8. I don't know what they do. Everybody's trying to make sure no one dies. So if you round that down, you're over-promised. You're under-promising and over-delivering. You're saying this is how strong it will be. So some of the things you see in your book are kind of hard to read for that reason, but notice you wouldn't be able to, if I asked you what's the slope of that blue line, you wouldn't be able to read that yourself. It's just too steep right there. Secondly, look at this. So this is a chart that I use all the time when I'm designing beams for houses, and I've showed you this chart before, but notice you're beginning to understand more and more about what you see here about these beams. And so let's take just to keep this simple, let's say we're looking at 1.5 inches wide by 7 1/4 inches tall. So it's a beam that, looks like that. And by the way, that's what a contractor would just call it 2x8. Started as 2x8, and then I mentioned that a little bit. They sand it down so it's smoother. So they sand off some dimensions on it. So, okay, cool. Well, notice here, this is kind of cool. It tells us how much that weighs. That's kind of cool to know. Pounds per foot. Notice that's not cubic foot, that's length. So they're giving me pounds. Every foot of it weighs almost 3 pounds. Oh, that's cool. I didn't know that. Can you appreciate that? Totally depends on what moisture. Like if it's outside in the rain, it's going to weigh more. If it's super dry, it's going to weigh less. That's a very randomish kind of a number. Does this mean something to you now? How much of this can a 2x handle before it goes? I understand that. Allowable moment. Do I understand that? How much can it go like this before it breaks? Do I understand this? Nope. Don't understand.
I was like, shit.
I wish I would have set that up before class. Had 3 of you go, yeah, we studied that. Cons are, damn, what's wrong with me?
I was like, don't call me. Nope.
No, that's actually the next project. I've got a project in mind after you understand this a little bit to look at. This number right here is the million PSI. That's the E number. It doesn't say that over there, but that's 1.7 million PSI.
So is the allowable moment in the elastic behavior, right? Like, because once it starts deforming, that can't be allowable anymore.
That's correct.
Okay.
Yeah, that's exactly right. So we're doing all of this in the area where we haven't broken it. As soon as we tear the fibers, it's no longer the beam that it used to be, right?
Nice.
So your dad falls off the ladder, now he's just never been the same. So notice right here. Exactly the same thing that was in the back of the book, times 10 to the 6th PSI. I actually like that better than times 10 to the 3rd KSI. I feel like I got to be double smart to even read that. This is just PSI, million. So notice some of the different readings for that, some of these different beams. The one we saw a second ago was exactly written over there, 1.7 million. This is 2 million. Notice quickly just at a glance, but it's like compression perpendicular to the grain, compression parallel to the grain. That matters a lot with wood. Does that make sense? If you have wood and its fibers are like this and you pull it this way, it's fine. But if you pull it this way, it splits right in half. That's how you split wood, right? Time to cut some wood. Do you split it with the grain or against the grain? Like, you don't want to get that wrong or you're never going to get the job done. Tension parallel, shear, like bending. So we're starting to actually be able to read stuff like this. Like, we actually kind of understand what we're looking at here. It's kind of badass, isn't it? So actually the only thing left we don't really understand is moment of inertia, which actually isn't part of this class, but I'm going to show you Thursday anyway, because it's too cool not to see. So that's a huge, that E number is a gigantic number. So all of those are just based on materials testing. But again, notice they're totally rounded off. It says 2 million. Is it 2 million? No, never is it 2 million, but around there, right? That makes sense. I
feel like all this like different specking is kind of reminding me of like, I looked at a chart for like different bullets and grain and stuff for each like rifle and gun. And it had like almost the exact same layout where it's like different grains and ranges,
Yeah.
like how far it
Yeah.
was. Like that. Now we're just doing it for
Yeah, that's totally right. There's like a chart that tells you how it all kind of works together and how far it'll shoot.
Yeah.
Yeah,
Pretty fun.
it's
I like
muzzle velocity and all that. Yeah, totally. Let's see if we can do a problem. 3.2, that must be the easiest one. Did I give you a copy of that? Did I give you 3.2? Okay, so this is kind of fun. And I'll admit, when I first stared at this, like, I was not getting these questions right. Like, I've been mentioning to you, I was studying this for quite a while, just reading it on my own and so forth. And I was just totally getting this stuff wrong. But notice there's literally a chart here of data. And notice what the data is. It is sigma and epsilon, like they're actually telling me the numbers. That's kind of cool. And notice one of them is KSI though. So that first one is really 33,000 PSI if we happen to care to know. But again, on a graph, it would make sense. I don't really want to have to write 33,000 on a graph. That's the, even write it down. And notice these are really small numbers. And of course, at a glance, can you kind of see the pattern? What happens as the stress gets bigger, 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 as you pull harder, harder, harder? What happens over here?
Proportionally.
Yeah, it's just getting longer, longer, longer. Now notice at this point, I don't know if it's straight line, but it sort of feels like common sense. Yeah, if I pull harder, 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 it's going to get longer, longer, longer. It's like, of course it does. It's not an inverse relationship. It's, what is that called? I guess it's not proportionate. It's directly, yeah, yeah. So, you know, the point is could I graph that? Let's see, what is it even asking me? Data taken from the stress strain test And can you appreciate that's what the machine would have to read is just literally some numbers? And at this point, I just have data. I just have the relationship, but I don't really understand what it looks like. Notice it says it's ceramic. That's kind of interesting, isn't it? As a side note, that actually makes me think it's getting shorter. I think if ceramics is not, or like concrete is not wanting to be pulled, it breaks really easy. So I'm wondering if this was under compression. The curve is linear. They tell me it's a line. Oh yeah, I kind of expected that. So this must be in that proportional. So they tell me it's linear between the origin and the first point. Oh, between the first point. Plot the diagram, determine the modulus of elasticity and the modulus of resilience. We don't know what the modulus of resilience is, but I'll show you that in a second. That's a 3.4 concept. So the idea is just, could I graph it? So of course, man, I got to think about the scale, right? What am I going to make each of these worth? So I've got to get out to 0.0022, or I'm thinking of it as like 22. So, what might that look like? So I would need to flounder at this sum. Do you agree with that? Like, part of me is thinking, well, if I need to get to 0.0022, then if I call this 0.002 and this 0.001, is that right? 1, 2, 3, 4, 1, 2, 3, 4. That's actually pretty close. And so, okay, so what does that mean? The rest of these are, so half of 0.001 would be 0.0005. So this would be 0.0015. That would make this 0.00025 and 0.00075. So it's like I'm just figuring out a scale to match the graph paper that I happen to have in front of me. And because I made this, I kind of took the time to make sure it would kind of work. But if I just had a regular piece of graph paper, I would have to kind of pick that scale myself. And so this is my epsilon. Epsilon always goes down there on the x-axis. And then sigma goes up here. And I guess I'll write KSI there because I don't want 5-digit numbers. And so I got to get all the way up to 53. So I got to go from 0 to 53 because this is 0 in both cases. So let's see, 10, 20, 30, 40, 50. I mean, I guess that'll work. So I'll call this 10, 20, 30, 40, 50. So, okay, cool. Everything I need. So now I start graphing this. And so I got 0, 0, and then 33.2 and 0.0006. And I'm not going to get this perfect, but because I could take the time to figure out what each of these little squares is worth, but I'm trying to find 33, 45 there for some reason. So let's see, this would be 35, somewhere in here, just roughly. And so they told me it was linear between there. And notice it's a good thing they told me that because that's a pretty far distance and I wouldn't have known what was happening in there. Is that curved? And so I could see now why they told me that was a straight line. And then because they said it's a straight line from there, I'm wondering if I'm going to start to see the curve after this, I guess. I don't, because they didn't say it kept on going straight. Just to save some time, I'm just going to throw this in randomly because I did this before class, but I guess I should do a little better. 0.001, I know exactly where that is, and 45.5, I can get this one pretty close. So I won't put any more points on there, but it kind of does this from here, kind of curves. So again, you can see I took the time to kind of give myself a piece of graph paper where all this fit. Does it make sense? I could have went to all that trouble and then the graph blew off of it. But remember, I did look at my two maximum numbers and made sure they fit. And so that's kind of cool. So can I determine E from this now? Now I literally had data. Can I determine E? Yeah, we just did it a second ago. If I take, I know this is 0, 0. So this distance right here, that height right there, we said, was it, since we were given it, right? I don't have to try to read that off there myself since that was 33.2. And this right here, even if I didn't graph it exactly right, was at 0.006. 0006. So we said that E was those two divided by each other in that particular order. which equals and because that 33.2 was KSI, this remains KSI. So do you agree that's 55 million PSI? Again, I don't work well unless I kind of go back to the original units. And so I find myself wanting to call this 55.3 million PSI, at least in my mind. I wouldn't see that in the back of the book, but I'd see the 55 one. I might even see 55.3 times 10 to the third KSI, which is annoying. So does it make sense? You could literally take measurements, graph it, and you could just observe how long was it straight, and right where it stopped being straight, hey, I found the slope, and now you have this magical E number. The bigger E is, the sort of the stronger it is. Big number, stronger. That's kind of nice. It isn't backwards.
Out of curiosity, it would be kind of tough to find out exactly when it stops being linear. Remind me, is there a calculus thing that I can remember that would give us the point in which it stops being linear?
No, because there wouldn't be one equation for it. Because everything you've ever studied was always one equation that may have had some cool wonky shape to it. But this is literally 10 equations. You have a straight line equation, and then you have this little curve, and then you have another straight line, another curve. Maybe this is a parabola. It would actually take 4 or 5 equations to describe that.
So we'll always, like, pretty much for our careers, unless we work for like personal line or whatever, testing the stuff will always be given when it stops being linear.
Yeah, you'll just be given E. You look it up in the back of the book, like that
Right,
table.
right.
It's just like, oh, what are we going to use? Steel. Okay, how much? What's the E value? And I'll show you how to use that Thursday to calculate how much something's going to deflect under load. There's a formula, a super simple algebra formula. So that's kind of cool. Let's see what else. And the modulus of resilience. Well, I haven't explained what that is yet. So let's talk about modulus of resilience. So really what we're covering here is kind of section 3.1 through 3.4. So let's see, I just want to look at something here. So I gave you this note sheet, which is what I showed you a second ago, except for this is what you're looking at right now. Mine was just blown up so you could see it a little bit bigger, but notice I went on. Basically, I showed you everything, at least we glanced at it. We don't own it yet, but I showed you all of this stuff sort of 1 through 7. But now look down here at modulus of resistance. Sorry, resilience. Notice again, hey, great, another new letter. Thank you for that. I'm really appreciative of that. You are a measure of strain energy required to reach the proportional limit. In other words, the light orange triangular area without causing permanent damage. In a sense, that's kind of what you were just asking, Connor. It's like, what is the strain energy that gets you to that location? Does that make sense?
Right, yeah.
It's like, how much strain can it take before it's like, oh, can't do it anymore? That makes sense. Because you notice you don't really care about the force. You care about how did it change shape, and when does its shape change be permanent? The force causes that. Yeah, they're related, but that's what. So, and of course, you understand, as a root word, what resilience means. Somebody who's resilient has overcome some challenges to be where they are, right? Which all of you have done just to be here. So that makes sense. How resilient is it? But the key is to reach the proportional limit. And that's a very important point because we always want to stay below that practically. And notice it says without causing permanent damage, which is kind of goes along with what it means to be in the proportional limit. If you go beyond that, it's going to cause permanent damage and it won't be able to do its job tomorrow. So it's that triangular area, the light orange area, and you don't see light orange in yours because that figures in your book, but it's basically that elastic region. So notice there's, well, kind of a formula here for it. And what is it calculated? It's the sigma squared. But notice it's those PL is not, that's not part of it. It's just saying it's the sigma for the top of that curve. In other words, it's the proportional limit. I mean, it's that point right there. It's what's that sigma right there. In other words, if you'd like to know what is this down here, if that's the question, because that's what modulus resilience is what is that point right there? What's the strain this thing can handle before bloop, it breaks? Well, this is saying, well, if you take that sigma up there, what do we do to it? You square it. And then divide by 2 and divide by the E value that you would look up in the back of the book. Isn't that kind of cool? Like you could actually just figure that out. You could calculate it.
So this is kind of just giving us our allowable moment, right? This is giving us the amount of force it can take before it begins.
It's not so much force, it's the allowable, it's a measure of strain energy. So that's like something lengthening. How much longer can this thing get before it's going to be stuck being longer permanently or the internal fibers tear apart?
So our units will be PSI over PSI, so this is unitless as well.
Well, that sigma is squared. So you have 2 PSIs on top.
So it's gonna be PSI.
PSI over PSI. So it's PSI.
But it's measuring.
But wait,
strain.
yeah, but it's measuring strain. So that's occurring to me right now too. Like, wait a second, I thought strain was unitless. And so I'm now asking the exact same thing you're asking. I mean, I guess it's not just strain, it's strain energy. Is energy?
This is how much,
Because I'm suddenly thinking, wait, that doesn't make sense.
how much can be pulled towards the reverse?
Well, let's let that hang in our brain a little bit and try to answer that with this question that we were tackling at least, and maybe our brain will, maybe between all of us, we'll figure it out. So modulus of resilience, this U of R. So there's more than one way to write it, but it's like the sigma of the plastic, or the proportional square divided by 2 times the modulus of elasticity. So, okay, cool. Okay, so, again, I like to look at algebra as recipes. And so, hey, look, this recipe calls for sigma of PL and it calls for E. Oh, look, I just calculated E. So that's kind of cool. I'm glad they asked it in that order because I now know E and I didn't realize that before. And so then the second thing I'm thinking is can I read that off the chart? Because notice they didn't just tell me this. They just gave me a bunch of data and they're asking, can I read that? Can I read that for myself off there? Well, can you? Like, isn't this the point right there? So this is where you've got to look at the chart. I mean, that's the sigma right there, where it stops being a straight line and starts curving, right? That's a specific sigma. So they said that's the proportional limit. That's the end of where it's straight. Oh yeah, I know that. So, okay, so you're saying if I take 33.2 and I square it and I divide by 2 and by E. Now notice I'm not being careful with units here because I'm suddenly thinking, oh, let's see, should I be doing this in P? My tendency is always want to change everything to PSI or something. But let's just think about what are these units? The 33.2 is KSI. So I sort of have like KSI up there for units because it's squared, right? And on the bottom, 2 is just a constant, so it doesn't have a unit, but 55,333 was also KSI. Okay, so those are going to cancel. So I guess my unit will be KSI when I'm all done. So I divide those, I get 9.96. So KSI, not PSI.
So I got 0.00996. And then I converted it to PSI, and I was gonna ask you a question about this.
Is, you squared 33?
That's right. 32 squared over. I put parentheses around 2 times 55, maybe that.
Yeah, I'm actually just kind of writing down what I had. I have a different unit on mine, actually, and I'm staring at it now going, what was I thinking? I have like inch pounds over inches cubed. Like I'm looking at that going, what the heck is that? Yeah, so you're right. I got 0.00996 KSI.
So it's
True.
good, I think. PSI, you have 9.96 PSI. So now I'm super confused on what that means.
Yeah, so again, these are both kind of true. Why, and I'm thinking out loud with you guys here. Why do I have written down inch pounds per cubic inch?
So the inches will cancel off at the top and we just put on the bottom.
So PSI is pounds per square inch, right? Are those the same?
Yeah.
They are if you kind of like multiply the top and the bottom by 1 inch, which is weird, right? Why would that be the answer? Why would the answer in the back be inch pounds per cubic inch?
Oh, because it's volume. It just gives it volume in the top one.
Say that again. What do you think?
Wouldn't inches cubed be something have to do with volume or mass?
Yeah, I mean, it's kind of, I mean, part of my thinking is, remember how we said E was, or epsilon was just a percentage? Like 0.0707%, but we also said sometimes, well, that could be millimeters per millimeter. Because that's still unitless, right? So part of me is thinking that's what's going on here, like it's epsilon, but there were never pounds in it, so I'm actually a little. I'm
So we
letting,
have stress as KSI and then epsilon is over inches. So that would give us pounds per square inch times inch, which gives us
yeah, it's like pound, like PSI millimeters per millimeter, or PSI inches per inch,
that's
something like that.
Uh,
Yeah, the answer in the back is inch pounds per cubic inch.
It's not ridiculous though, because our place is just gonna.
That's hurting me, yeah.
Yeah. It's pretty-
I mean, I'm finding myself sitting here thinking out loud, it's like,
Why would they
what
clean
exactly
that up?
is strain energy? I guess I'm thinking it's
Well, on the
strain,
back
but it's
end-
like how much energy. I mean, I guess the PSI force, maybe that's it. Like you have the PSI force on it, and that's kind of, you know, the sense of energy. It's like if I'm pushing on something, I can think of that as being like energy I'm putting into it, right? And as a result, it changed shape by so many inches per inch. I guess I could see maybe that.
Oh. So that is how much force it takes to change it 1 inch, like how?
Yeah, like inches per inch.
Oh,
It's like that's how much force it takes to get it to
that would make sense
strain,
why it's so small too. 'Cause that's my,
strain that much.
that's my thing. I was like, I thought it was taking us directly to the top. Like this is how much it takes before it starts changing permanently. But the way you say it makes more sense.
So that's actually still bothering me some. I mean, as far as what we're understanding right now, like to answer that as KSI or PSI would be okay, wouldn't it? It's not like that's wrong.
So, yeah, I was, okay. So if I put in my answer PSI or KSI, and then I look back and see that one.
Mhm.
I wonder why they're keeping it like that. That makes no sense.
So, you know, this, because this is, one of the things I try to do with these note sheets is kind of give sort of an explanation. So I said it's a measure of strain energy required to reach the proportional limit energy, but I'm finding myself thinking, I guess I don't really have a good feel for what strain energy is. I don't really feel like I have an understanding of that.
Energy dynamics.
Yeah. This is not good, right? We just studied energy and dynamics. This is not good.
Better than the class right now.
Yeah.
Oh, no. Let's see. And also I have a very, you may have noticed on the syllabus, there's like a whole bunch of holes in the time. Like, what are we gonna do that week? There's nothing there. I don't really have any sense, like I want to spend enough time with what we talked about today that you kind of understand the stress strain diagram. I really have no idea how long that was going to take. So I think we're going to end up, the syllabus will flesh itself out in this class more than it usually does. I'm usually a lot more on top of it. Let's stare at this for a second without doing this question just yet, because I think we have time for one more, maybe two. Do you see how this is what I was showing you earlier? Like that's the same exact graph right there. Over here, this is so steep, you can't even see it. And that's the black numbers.
Can't even see where it levels out either. It's like one big curve.
Yeah. And so this part up here, I'm like, oh yeah, it curves, it reaches a max, and then it comes down and breaks. I'm kind of okay with that. But it's like the most important part of this graph is this part right here, which I can't even discern. And keep in mind, that makes sense because it's tiny, right? Like if you put pressure on something, if you haven't broken it yet, it's not going to change length very much. As soon as it starts really changing length, you're kind of breaking it, right? So then down below, and notice the coloring of this is just horrible. Like at least if this was green and brown or something, but it's like, this is terrible. This light blue is the same color as that light blue, but they picked light blue for the other one too. That was brilliant. Brilliant. Like at least go black because the numbers in there are black, but I mean, this was hard for me to understand, like personally for a while. I'm kind of a slow learner too, but it's like, that's not very good. But do you notice without really paying a whole lot of attention, it's like, oh, okay, here's the proportional area. And then it started, behaving differently after that. Notice I can't really see a curve here, but it's like, oh, whatever. Notice the units haven't changed. This is still inches per inch. And this is still KSI. We're never going to have something that's like 13 PSI. Nothing is that weak. It's always thousands at least. So we're talking about 60,000 PSI right there. And we haven't even divided it by the strain, which is tiny, which is what makes E so large, right? So this is kind of cool. Stress strain diagram for a steel alloy. Don't tell us which one it is. Had an original diameter of 0.5 inches, and it was 2 inches long. And notice that's exactly what I showed you in that picture a minute ago. They're a ½ an inch in diameter and they're 2 inches long. And the stuff outside of that is just there to support the process. So it's kind of like a little cylinder. So determine the approximate modulus of elasticity for that material. Oh, I could do that. That's easy, right? I can read that off. Notice they said approximate. Why did they say approximate? Because I got to read it myself. Last time they gave us the reading, right? They cheated and gave us the reading, where this time I got to read it myself. Well, it looks like it hits right on that point. So I'm probably going to get a pretty good answer for this. So is an E 40 over what? Yeah, over the lower reading. So it's 40 over 0.001. 40 KSI over 0.001. So that would give me 40,000 KSI. Or, is that right? 40,000 or 40 million PSI. Have that right? Dividing by 1,000 adds 3 zeros, doesn't it?
So it should be.
So the unit of 40 was KSI, so it stays KSI. All right.
Now you added zeros to PSI.
So I could say 40 million PSI if I wanted.
But if you have 4
It's
Yeah, I think it's 40,000 PSI.
It's 40.
It was already KSI,
And then if you add.
but then I divided by 0.001, which made the number 40 turn into 40,000, so it's still KSI, all
There we go.
right?
You're good.
Hasn't changed.
I thought you were converting the 40 to 40,000 PSI, but you put KSI.
It would help if I actually did the problem with you. My bad.
But see, then they ask some other things like, okay, I'm getting E figured out. And as far as like stuff you leave this class knowing, you're there. Like an engineer is going to stay here. All they need to know is they don't need to know all this other stuff. However, you can appreciate if like some bridge was starting to collapse, like maybe that would be where you'd be looking in the rest of the chart. It's not like that's totally irrelevant. So they say determine the approximate modulus of elasticity. Okay, that's cool. I got that. And then they said, what's the load on the specimen that causes yielding? That's a key word, I suppose. And the ultimate load it will support. So I want to give you a second, because this is really like how to read that chart, that not colored chart that's actually colored. So they're talking about yielding and ultimate load. Notice they didn't say, notice they actually did not say the ultimate stress. They didn't just say read the chart, they said load. What the heck does that mean? What's the load for yielding and what's the ultimate load? What's the most load you can put on it? So I just want to give you a second to think about that before I do it with you. So from your graph, would you agree that this highest point up here, wherever that reached, that's kind of the ultimate? That's the highest point it reached. You see how it's going to be an estimate? None of us are going to get the same answer for this. But it didn't ask for the ultimate stress. If it was, I'd say, oh, I don't know. Actually, notice I did a bad job with my red line. Would you agree that my dot over here is above halfway, but by the time I get over here, it's below halfway? Again, who cares? But it's probably more than half. So I'd say 76 maybe. So I don't know, let's just pick that one. So they didn't say what's the stress, because if they did, I'd say 76 KSI and I'd be done. They said load. What does that mean?
Force of pi over area.
Yeah, isn't sigma a force divided by an area? Like the N is the force. That's the load. That's the weight. What weight would cause this? Again, that's pretty cool to think about, because you can't just say, you know, when you drive your truck on here, make sure it's less than 76 PSI. You have to say less than 50,000 pounds. You know, it's like up to you to make that calculation. Well, notice I realize now, oh, they told me the diameter of this thing was 0.5 inches. And we said if you take pi over 4 times the diameter squared, that would be its area. And then I could calculate that normal force. So if I take 76 times pi over 4 times 0.5 inches squared, then I actually be able to calculate the force that it would took to get it there. So again, that's pretty cool ahead of time to say, oh, look, I tested this material, I have all this data, and now I can say how much force I can put on it, given that it's a half an inch. Given this half an inch, I'm saying if you put more than that on it, it's going to break. It's going to reach its ultimate. You can't put more on it than that. So if I solve that, I get, and it's about 14,923, I guess it would be pounds, wouldn't it? Because the bottom of that is square inches and the top is pounds, so N is pounds. So I'm having to read that chart. I'm having to know where sigma ultimate stress is.
So for.
Where's yielding? Look at your chart. Where's sigma y? Where's yielding happen?
Maximum load before it levels out, before it can enter that.
So it's like this, right? So it's kind of like right in here. Does that make sense?
But ours doesn't have that. It just has like a point.
That's exactly right. Ours doesn't have that cool little curve, does it? So it's like, so it's kind of like, you know, they're distinguishing here between yielding stress and proportional stress. But we just kind of have a point, right? It's not so around there, you know, around there, good enough. In my case, I'm thinking, well, isn't that kind of right around there, like 40? Somewhere around 40, close enough? Yeah, that's exactly right. So that calculation is the same. So if I take sigma of yielding equal to 40 KSI, and that is equal to exactly what it was before, n divided by pi over 4 times the diameter squared.
Did you multiply 76 or 76,000?
Yeah, because this 76 was KSI and it bothers me. I thought of it as 76,000. So that's why I got pounds, not kilopounds. So the answer in the back of the book for this would probably be 14.9 kips, kilopounds.
Way bigger number than 14 million.
You got to be really careful with the algebra to get rid of pi over 4. Did you take 76 times pi divided by 4 times 0.5 squared?
Just straight across.
Because if you did that, you should get 14.9 or somewhere around there. And that'd be kilopounds because 76 was pounds per square inch.
So this is picking up.
Isn't that right? Go ahead.
You're supposed to just multiply by pi over 4 as a whole.
Yeah, I mean, you can do it as a chunk.
For some reason, I thought I did that and got the wrong answer. So I started doing them separately. So I multiplied by 4 from the numerator and on the opposite side, which was.
Yeah, you got to be really careful. When it's a fraction divided by a fraction, you can easily screw that up because you should be dividing by 4, actually, not multiplying by 4.
On the top. I get it.
If you want to leave it on the same side, then you could multiply 4 by n, like it could become 4n over pi times 0.5 squared. Just simplifying the right side so you don't have
can just
fractions
keep it
over
as a
fractions.
whole, right?
But you can just keep it as a whole and say times pi over 4.
That's what I'll start doing.
Yeah.
That's
That's
way easier.
surprisingly tricky. I completely sympathize with what you're saying there. So in this case, I get something similar. Because 40 is kilopounds per square inch, I get 7.85 kips. If I think of 40 as 40,000, then I get 7,854 pounds. Approximately. I mean, those are both fine.
So the bridge would say, don't exceed 7,800 pounds.
Exactly. That's exactly right. So really, that's our limit. That's our realistic limit as an engineer is that number right there.
So what,
It's half an inch. It's not
so why do you go to plug that 40 in? Or why do you multiply by the 40?
You're not multiplying it.
Go ahead. Ask it again. I can.
Me and Caesar is confused why the 40 is, like, what's that equation look like bare bones?
I think I need an equal sign right there.
Oh,
I got
Yeah.
excited.
oh,
Sorry about
Oh, okay, that
Sorry.
was me also.
that makes sense.
Yeah, now I know.
that. Kind of changes things a little bit. If you guys had a good teacher, you wouldn't have that problem. So do you see, that's kind of a good question to ask because both of those are particularly interesting force calculations or load calculations. One of them is to stay inside that proportional area. Connor said it's a good point. Really, the limit of this would be 7,800 or 7,500, you know, round it down, something like that. And then as long as we keep that, then great, awesome. Remember though, that's on the 1/2 inch member. In other words, it stayed 1/2 inch. So as long as I keep less than that, it's going to be just fine. And you can imagine a 1/2 inch bar as being, and it's a fairly significant size. It's like the size of your thumb. That's a significant bar in support of some kind of a structure, and saying, okay, as long as you got less than 7,500 pounds on that baby, it's gonna do the job.
Eventually, like if it's long enough, would it just fall apart?
No, that's interesting. With respect to tension, it doesn't matter. It could be 40 miles long and it won't matter. Doesn't make any difference that it's long. I mean, in that much distance, there'd probably be some place that was a weakness in it, like some dirt got in there, that kind of thing. And where it would matter is compression. That'd make a difference, because if you pushed on it, it would go boom, bend out. So compression, it actually matters how long it is, but not tension. It's interesting. Let me see what these last two questions that I had planned to talk about today are about, and we'll decide whether to put them off.
More problems. It's just,
Yeah, we need to do these, but let's just pick it up next time. But at least stare at this one to notice this is really cool, because it says this rigid beam is supported by a pin at C and an A36 steel guy wire. It's like a certain kind of steel. Does it make sense? I could go to the back of the book now and look up what the E value is for that, because it's a certain kind of product. And so this is starting to get pretty real now. Got this certain E value that I'll be able to look up in the back and, you know, make some calculations off of this. I'm likely not going to give you any questions like those last two on the test where you're kind of reading stuff off a graph. It's kind of cool to understand that, but I think that's absolutely worth an assignment question, but I don't think it's worth a test question. Whereas this is the same concept. It's just now we're back to pictures that we recognize and so forth. So notice it's asking, determine the distributed load if the end B is displaced down a certain number of inches. So it's like, yeah, that's a strain related question, right? It got bent down a certain amount. Now we're actually saying what kind of load would cause that. We're relating strain and stress here for the first time. We aren't just saying how much longer would it get, leaving it at that. We're saying based on the kind of material with a known E value, the backbone of the equation, you know, that we've been working with is that guy. So if I know two of those three letters in that nice simple formula, I can always calculate the third. And remembering that, you know, this is N over A and so forth. It's like I can start to make some pretty realistic calculations. But anyway, let's pick that up on Thursday. See if we have time to do this question, and maybe that's it, or maybe this question in the next one, and then we'll work on the kind of the practical project. Looks like those are pretty similar.
Doug, could you do me a favor and pull up that lumber chart one time?
This one?
No, with the
Oh yeah. This one.
Tom.
Hmm?
You look like you got a 1.7 grade. Because you're a versus stud.
Yeah.
All for that.
I was.
1.7.
Yeah, you're like, I thought about that midway through and I was like.
That was great. That got me off guard.
Oh my God, that was terrible. Jim Oaks put this signal. I didn't even know friggin' iPhone
I
had
left
that.
it out there, copied it.
Oh my God. They're like, man, I'm really sigmaed out for these tests coming up. And I was like, oh my gosh, I'm gonna vomit. So cheesy.